my idea was to perform, use scales theory tools to study the system. So, my previous works had been with one-dimensional partial differential equations. So since this is a much more complex problem, I had to balance how realistic the model would be. So the Reynolds number is about 100 and the forcing scale, or 500 in the box scale. So it's not so big. It's 100 in the forcing scale, so not so big, not so low. Because if it goes so low, very low, then your dynamics reduces to a low-dimensional dynamical system. And that's not new. So if you go too high, then you don't understand what you do. So it's difficult to do dynamical systems analysis. Well, at least in the first attempt. Well, the motivation is an intermittent solar cycle. Although I'm not simulating the solar cycle, it's not a butterfly diagram or something, but perhaps the type of intermittency that I am observing in these simulations have something to tell what the solar cycle. But you need that to publish papers, you need motivation. So this is motivation. For me, motivation is just mathematics, because I'm in the mathematics department, so the equation itself is motivational enough. The problem is periodic boundary condition in this box, helically forced by the ABC flow, ABC forcing, so it's isotropic. And I'll do a computation of finite time Lyapunov exponents. I don't know how many of you are familiar with Lyapunov exponents, so it's basic tools for chaotic systems. So I'll give a brief definition. And then we have a transition to intermittent dynamo. So I'll study the transition region from no dynamo to onset of dynamo. Okay, and there is intermittency in that. Okay. You have what is the definition of intermittency that I'm using? It's very basic, very rough, and not precise, because it's something like this. Intermittency is characterized by time series with random switching between phases of lamina and bursty behaviors. In this case, lamina should be something like the moment minimum. It's a lamina behavior, weak oscillations of the number of sunspots or something, and the burst is whatever else is not lamina. So you have some minimums, some minima, and if you go backwards in time, you check the history of sunspots observations and naked eye observation by ancient Greeks and Chinese. You go backwards until 500 before Jesus Christ, and you have I don't know how they did it, but they have this account of the number of sunspots. The table is in Whitman 1978. So you have well, you can go backwards in time using proxy data until 5000 BC, I think. But even if you start just with historical data, historical observational data, you can see some minima in the time series. This is from the naked eye observations, and from the telescope era onwards you have better data. But and this is the proxy data used during this period. So carbon-14 measured from tree rings of very old trees. So the level of carbon-14 is inversely proportional to the solar activity. You can identify the minimum. So there are several minima identified by Eddy and some. No, this is not Eddy. This is Voss 96. Number of minima. So it gives you an idea that it's a repeating event. From time to time, you have this minima, this minimum, and then you have bursts, minimum bursts. So that's the intermittency we're looking at.
But it's not random, right?
Sorry.
If you look at sunspot. Geometry to show again. It's not random.
No, not really, but
you can see then longer time periodicity, longer periodicity.
Yes, but you cannot.
But you cannot say it's a random behavior.
No, yeah, random is just not the correct word. It's just to say that it's not periodic. Okay. Although there is an average period of 200 and something years, but if you check the distance between one minimum and the other, it's not periodic, right? There's some order, but it's not periodic.
Well, then we have the question of how reliable this is.
No, yeah, nobody does because it's
But if you look at the modern records, for 100 years of transport, it was very, very periodic, it was 11 years period.
Yeah, you can find, depending on the model, of course, yeah.
And for some modulation, with some...
Yes, but you find some models where you have a very, very incoherent distribution of minima.
No, just,
They don't fit the observations.
But the observation goes back only to this. You
No,
don't have enough.
no. 11-year signal is seen
Oh, no, yeah,
in
okay.
proxies for a century, thousands of years.
Yeah, you mean
11-year signal.
Yeah, okay.
We don't discuss the amplitude, but the period.
Yeah, the period. Okay, but I'm talking about the minima, not the source. Okay.
Okay.
Sorry. The minima are very chaotically distributed.
But amplitude is random.
Yeah, amplitude is also chaotic. This is not a
More or less.
periodic time series.
It's not quite random because
No, it's not random.
You've got against quasi-periodic, but not purely periodic behavior. So,
Yeah. If you strictly speaking, it's not periodic because if you check the amplitude, it's not periodic. But then in time, it is periodic.
Well, some people question the accuracy of these measurements.
Yeah.
If you look in the past, the records, not that regular. If you look at modern data, they're much more regular.
But the amplitude of the number of sunspots varies of.
that would be artifact of the data.
Well, the number of sunspots is also not a random number.
No, but it's not periodic also.
it's not periodic.
Cannot be.
Alexander, it's a simple question. Is it periodic or not periodic?
No, it's not
It's
periodic.
quite periodic,
But
right?
it's not random. Now, question of this random switching and all that solution.
I mean, Rico was never saying that it's random.
What sense random?
I mean,
Like it's an intermittent.
but what do you call it then?
Say it's random and it's
It means random, not periodic.
It's non-linear.
Right?
Neither the random nor
Okay,
periodic.
that's nobody complains about that.
Well, perhaps we should move forward. Okay, that has led some people to study this distribution of the. Let's focus on the minima, not the 11-year cycle. Okay, the distribution of the modern minimums. And time, they have studied it using chaos theory. Okay, because in chaos systems you have intermittency arising naturally at some specific situations. The model is this, so using the pencil code. What is to be observed here? Well, we have a forcing here, which is the ABC forcing, and joules in isothermal gas because of simplicity. I think that's it.
So A, B, C coefficients are random, yeah?
No, they are this, okay?
Just regular.
Yeah. Helical, and it does exhibit Lagrangian chaos. Helicity is important because of the alpha effect, and then you can potentially show mean field dynamos, and the chaotic behavior is able to excite a small scale dynamo. So because of the stretching, twisting, and folding of magnetic field lines. So this is important to have chaos and small scale fluctuations and chaotic fluctuations, and also a large scale dynamo because of helicity. That's the reason I chose the ABC flow, and also because it was very simple and very well known. What else here? 2 pi periodic, and the amplitude of the forcing is chosen as in such a way to keep the Mach number below 0.4, I think, in this case. So it's weakly compressible, and that enables me to use a low resolution. Is this resolution enough? Is it big enough? I'm not sure, but I have computed some cases with a double resolution, and they seem to give the same average values. And well, what you could have with larger resolution is a shift at the point of transition from to dynamo. But I believe the bifurcation that generates the dynamo is a blowout bifurcation, even if you increase the resolution. But that has not been verified. The forcing scale is chosen as chi k equals to 5, which is the average, the characteristic weight number of the turbulence. So this is ABC flow, So at a low kinetic Reynolds number, you see the ordered structure. So your velocity field, this is without magnetic field first, okay? Purely hydrodynamic simulations. Your velocity field will converge to a stable state, which is, yes, it doesn't change with time. So it's a steady state and it's fixed point of your system, if you prefer to call it that way. If you increase the Reynolds number, then the ABC flow becomes unstable. It's a solution of the system, but it's an unstable solution. And then you have a sequence of bifurcations to periodic behavior, quasi-periodic behavior, chaotic behavior, and then all of a sudden you have a spatial temporal chaos. You can quantify the level of chaos with the Lyapunov exponent. And that's what I have done. Actually, well, this is just another way of seeing things. This is a two-dimensional slices of it, showing the stream lines. The good thing about this line integral convolutions is that you can see the dynamical structures very well here. You can, well, for people who have been working with chaotic systems, you can identify subtle points here in our clinic connection. There's another one here, and several subtle points. So it's beautiful. For me, it's a good way to visualize it.
What is unstable Reynolds number? What is
Reynolds number here is
stability? What is the
for the stability of this flow. I don't remember this. It becomes unstable at 20 maybe, or 10, between 10 and 20, I think.
12 is stable according to this picture, at least.
Yes, it's stable here.
Yeah.
Yeah,
So it's
stable.
more than 12.
Yeah, more than 12, sure.
Yeah.
Yeah, I think it's close to 20.
Yeah, I mean, if you actually were to divide by 2 pi, I think the critical number, according to a paper by Podvigina, I think is her name.
Yeah, she did a bifurcation diagram, but she was forcing at scale k equal to 1, the largest scale. This is k equal to 5, it could change the dynamics. So we don't have a bifurcation diagram for this case. And she did it with incompressible flows.
Yeah.
So the Lyapunov exponent, finite time Lyapunov exponent. Well, this mathematical description you can find in any standard textbook. It's basically, the basic idea is like, suppose you have a sphere of initial conditions of particles that you're gonna drop in the flow, and you're gonna see how they expand. So the flow is going to deform this sphere into an ellipsoid figure. So the axis of this ellipsoid could be growing or shrinking with time, and this growing and shrinking is the rate of expansion, stretching or contraction. And it gives you the idea of stability around the central particle in this middle, okay? So if you have a positive Lyapunov exponent, it means in a certain direction, it means this ellipsoid is expanding with time. So you have instability and particles are diverging. So if you have only negative exponents, then it's shrinking. So a good way to interpret this, well, first, the results for the stable ABC flow, you have chaos. You have this very weak chaos. So there are some chaotic regions in this velocity field. So if you sprinkle several thousands of those initial conditions, spheres with initial conditions in the velocity field, and compute the Lyapunov exponents, and then you make a PDF and calculate the average values, then you have small chaos. So there are some initial conditions that display chaos, some others do not. And well, this is actually the first, second, and third Lyapunov exponent. So there are chaotic regions, and for higher Reynolds number, you have a very stronger chaos. So you have more spreading of these particles in the passing spheres in the velocity. Okay? All this is big before inserting the Lyapunov the magnetic field. So if you have 3 positive Lyapunov exponents, it means your velocity field is expanding in all directions. It tends to dilute out the magnetic field. 2 positive and 1 negative means you concentrate magnetic fields into sheet-like structures because you have 2 directions of expansion and 1 of contraction, and you have like a sheet, right? And if you have 1 positive and 2 negative exponents, it's the tendency is to magnetic fields to concentrate in narrow ropes because so only one exponent direction, right? Three negative exponents, it's compression in all directions. Later on, I'll show
How
a
do you
picture of that.
calculate these exponents from this result of principle?
The physical. I could show you how to do that. You have to. Well, I don't know if you can insert the computation and the code itself, but you can save long time series, spatial temporal series. Actually, you save the snapshots of the simulations with a very small time step between one and the other, so like 0.5, and then you do an interpolation between them. You have a continuous spatial temporal series. But you need also interpolation in space, not only in time. Because you need a continuous in space also to compute the trajectories of the particles. And then you can move backwards and forwards in time, as it will.
So you trace particles, put some particles in your flow and then you trace them, or how do you do it?
You can insert a particle in this.
So particles, when you trace particles in your flow field?
Yes.
That's how we do this.
Yes.
But how is your particles,
Well,
how choose where you insert the particles?
Sorry?
Describe this procedure, because you have to put some,
No,
particles in your flow field and then track them and
Yes.
to do transfer.
Yeah, you have just this. You have like right?
Yes,
You choose the initial condition, and then you go.
But how you choose initial conditions?
Oh, you spread them. And
Just randomly at one moment of time, or?
you choose an initial time, yes.
Uh-huh.
And then you put the initial condition. So you're measuring the finite time level of exponent, not the long time level of exponent. The finite time at some initial. Suppose you have this.
Because it will depend on how you choose the initial
It
initial
depends,
time.
of course. It depends on the initial time, and depends on where you put the initial conditions. So what do? You spread thousands of them in the box, and you compute averages.
In different times.
You can do different times and then and so forth. Yeah. If you want to study just this initial, suppose I want to know what is the finite time level for this initial time. Okay, I can do that. If you want to do the time series average, then you have to sprinkle in several different ones.
It's like millions here, right?
So you average, of course, over different trajectories,
Yes.
right?
Yes.
And then you could take different moments of this average.
Yes.
You can take, for example, up to the maximum, or you can take lower. Maximum means the infinite moment, but you can take lower moments, of course.
Yeah.
And the spectrum of those results is what is called the spectrum of topological entropy. I mean, the zero one, I think, is the topological entropy, and
The
the
zero.
general spectrum is simply the generalized entropies.
I'm not sure. No, I don't know.
We calculate that in '95 from convection simulations. So you just take the average, and we calculated the level of exponents from the derivative of the Cauchy matrix.
Okay. I can check that.
That's the simplest part.
Okay. Let's move forward.
You have a periodic boundary conditions here.
Periodic, yes.
So what happens if particle goes
Yeah, they-
outside and then comes back, so
You have to be careful with that also. Whenever the particle is going out of the box, you have to insert it the other part.
You calculate trajectory for each particle.
Each one, yes. So this is the bifurcation diagram. So red is magnetic energy, black is kinetic energy. So for eta, this is the real number, this is eta. So as you decrease eta, at some point, so insert the seed magnetic field, they will decay to 0, but at some point, eta equal to 0.053, the seed magnetic field will start to grow, okay? Will grow and then saturate at some point. So the magnetic energy will increase with the function of eta at the expense of the kinetic energy. What happens in this region, close to the transition?
What's the difference between two graphs?
It's just log scale here,
Ah.
just to see this. Well, So at 0.055, so this is like here, before the onset. But you already have something. The seed magnetic field starts growing and but then decays. So it's like a transient dynamo. It's not a dynamo really. It's just transient behavior, transient chaotic. This is for different initial conditions. You see several different initial conditions. You have transient chaotic behavior and then it goes down.
What was the seed field?
Sorry?
The seed field.
Seed field is about 10 to minus 5, I think. Yeah.
Just random numbers?
Yeah, random numbers, yeah.
There was a paper by Galanti, Soler. They also use ABC flow and they consider they found dynamo and then situated what is the difference between your simulations and
Well, in this case, I'm not sure if I included that reference in the paper, but I hadn't seen a case like this with a forcing scale equal to 5, because you can have the inverse scale of energy, and also compressible, and incompressible.
yeah.
Oh, and I think Galanti used the forcing scale of 1.
Yeah,
There was no
I think
scale
most
separation.
people do that.
Yeah.
So then there's no need for dynamo.
Mhm.
You need at least 2 to 3.
In addition, we with Galanti used non-Ampere non-linearity, but full linear non-linearity.
So if you decrease from eta 0.055 to 0.053, you have already the dynamo, the magnetic energy does not decay to 0, although sometimes it gets very close to 0, like Monde behavior, okay? Similar to that. So this is what we call on-off intermittence, because sometimes it's on, sometimes it's off for a long period. You see 15,000 times to 20,000. Here the turnover time is about 3 point something, so you get an idea of the time scales. If you decrease the eta to 0.05, you have this, and then the energy doesn't go so close to 0. And if you check the spatial structures in this other case here, they're very different from this. Let's see.
May I ask a question to Sasha? The bottom plot, is it random or quasi-periodic?
Oh, they're all random. It's not like a sunspot number. We cannot compare with solar cycle. It's nothing to do with solar
It's
cycle.
not so it's more similar to Earth magnetic field behavior.
I don't know what maybe it's just it has no relation to any kind of
Real dynamo.
most likely. Physics is totally different, I believe, for the solar dynamo here.
Great, yeah. There's no rotation, there's no shear, there's no convention. First step, this is first step. Just definition of blow-on modification is not so easy. First intermittence, the on-off. You have sometimes very weak magnetic energy, and then strong magnetic energy, weak, strong, okay? And but check the spatial structures. They are always disordered, okay? Disordered, and it's difficult to see here because it's too bad, but it's also disordered, believe me. But the other one is different. At 0.05, you have order. So the magnetic field tends to self-organize to some direction. So here it's aligned with the Z direction. Okay, you have strong here and low here. Okay, and then it breaks the symmetry and becomes disordered at some other time. Then at t equal to 9,000, it self-organizes again, but along Y direction. Then breaks the symmetry again. So it's different, spatially different from the other intermittency. Okay?
You included here compressibility. Have you compared the simulations with
Without
compressible flow? What is the role of compressibility?
Yeah, I don't know yet. I have to check it.
For example, for small-scale dynamo, we know that compressibility causes increase of threshold of excitation of small-scale dynamo. But what here? I don't know.
I have no idea.
How we measure coherence here?
I can measure with spectral entropy. If I have time, I can show you later, because it's very different. If you measure the spectral entropy between two time series, it's totally different.
Mm.
So entropy here is much lower than here.
And there is some lifetime for these structures?
I have run it till 30,000 time units, and so there's millions and millions of time steps, and they keep doing this, switching. They don't choose a wave number. So, oh, sorry, an orientation. Wave number is okay. At some point, 0.01. So at this point, magnetic energy is about the same as the kinetic energy. Okay. So then the magnetic field settles down to one particular position. It could be Y, Z, or X, depending on the initial condition, but it stays there, okay? And then it just moves. This is just, forget about this. Let's see the movies. So this is the first one, the first intermittent. No, sorry, this is the second one. The first is no fun. Okay. You see, sometimes it's this way. Let's see it starting again. Okay. Here you have. This is not the best one. I have a better one. Sorry. Okay, very clear now. Sometimes this way, sometimes this way. Yeah. This way. It starts again, and this way, this way. If you keep doing switching,
It never goes now.
sometimes it breaks.
Never go on this way. Right.
It could go, but not in this. This is it shows just some frames, but if you go, I don't think there is a block in some direction. I have no explanation for this yet, but I have some theories that, based on merging prices.
Sorry, this is magnetic field?
Yeah, BY component of the magnetic
BY. Okay. In principle, ELE studies with ABC field show the structure of magnetic field like cigar-like.
No, that was the velocity what I showed you. I didn't show you the magnetic field for because once I forgot about that ABC flow because I increased the Reynolds number and it became totally unstable.
Okay.
So the velocity field is not ABC flow anymore. It's some spatial temporal chaos states.
But maybe in linear stage.
Then you see, it chooses this direction, and then it just oscillates around it. This is for eta 0.01. You don't see the switch anymore. Okay. Well,
They still can see ABC flows.
there are some features of the flow that emerge sometimes because it's still forcing the fluid. Yeah.
If you average this picture, I mean this big wire, what's the typical scale? Scale of
The scale of the box, yes.
it's not how to say homogeneous.
No, it's the scale of
So
the box.
it's not periodic. It means on one side the same field as on another side.
Sorry.
Is it periodic with infinite period maybe in space?
In space, it's like well, I haven't done this, but from the picture it seems to be like.
But if you average, it's interesting picture.
Yeah,
If
sure,
you-
sure,
If it
yeah.
will be homogeneous, you find something similar to large scale dynamics.
I should do that.
But what is the question? I mean, of course.
If
it's
you
not-
average this in time, say, and after that
Ah.
in plane x, z, say, so you've got just or when
Yeah.
it
Then,
just y is function.
I mean, in this case, clearly, if the
It
orientation.
should be homogeneous or quasi-homogeneous part. So it's large-scale dynamo. Very interesting to check it.
Yeah, but of course, the answer must be yes.
Yes.
In forcing scale and in small scale.
And forcing it small scale.
Forcing it's like this.
And
You see, forcing is here.
of course it's helical.
But
It's
the magnetic
it
energy,
should
the
be
peak is
just
here.
square dynamo in some sense.
Yeah, but why is this
Because
right?
it's helical, you know, it's a helical. This ABC flow is helical flow, it's maximum helical flow. It should be dynamo.
Yeah, but of course.
Yeah.
So no.
Okay.
It's similar to some result that the Axel published.
But it's not the same. It's alpha square dynamo, not because you haven't sure.
Yeah, this is alpha squared. Yeah.
Not that one.
But he had a paper with alpha squared also that generates some similar results. So forcing is here. You see velocity field is dashed. The magnetic spectrum is dashed line, and red is magnetic. So it is the scale of the box.
So that's exactly the case where you see the catastrophic quenching. That's exactly where it comes from. This type of work.
Well, yeah. The rest of it is Lagrangian coherent structure. So I don't know. Maybe.
Actually, you
Should
mean
stop
the
here.
catastrophic quenching here, there is a strong quenching of alpha effect?
Of course.
How can I explain the structure?
Well, we could if you want. It's just because of the time today. But so what? Should I keep explaining the structures? What do you, okay. Okay. Let's go back. So what are Lagrangian coherent structures? Because when you're describing dynamical systems, you tend to use describe it in terms of what they call the skeleton of a dynamical systems. It's like unstable periodic orbits and their stable and unstable manifolds. So like saddle points and their manifolds. A saddle point is a fixed point solution of a dynamical systems, which has two specific directions, one which is attracting, one which is repelling. So if you were to compute the Lyapunov exponent nearby this saddle point, using this idea of finite time Lyapunov exponents, suppose you have two particles here. They will follow this dynamics. This one will go this way, and this one will go this way. Because of this direction, the unstable manifold will push this particle to the other direction. Okay. So if you compute the Lyapunov exponent, like of two particles here, they'll both go this way. So the Lyapunov exponent is not large. Even it could be positive, but it's not very large. We go this way. If you choose two in this, so it's very large Lyapunov exponent because they depart from each other exponentially fast. If you run the system backwards in time, and you start with two particles here, go backwards in time, one will go this way, one will go this way. So what does that mean? If you compute the Lyapunov exponent backwards in time, you'll find these unstable lines, the unstable manifolds. If you compute it forward time, you'll find the stable manifold. Okay. Take this snapshot for instance. Suppose it's a two-dimensional velocity field and it's steady. It doesn't change with time. So suppose that's the case. You can find a saddle point here. You see, there are some points that go this way, like. So you see, there is the stable manifold and unstable manifold. Particle here go this way, this way. Okay, and this is a fixed point. It starts here, it stays there. Okay, this is a saddle point.
It's like a separatrix?
Yes, separatrix in your velocity field. But now, suppose you have a three-dimensional velocity field, so it's not so simple, and it changes with time, so those vortices don't stay steady there. So you have a confusion, but you can still compute the Lyapunov exponents forward in time and backwards in time, and that's what they call the Lagrangian coherent structures. What are the Lagrangian coherent structures? Are the equivalent to those manifolds in this time varying velocity field, okay? And you have something like this. This is for no magnetic field and Reynolds equal to 100. You have strongly chaotic regions with several of those lines, and they are crossing, and you have strong chaos. If you check the Lyapunov exponents, 0.34. So you have strong chaos. This is good for chaotic mixing because the particles follow the green lines and they go on towards the red lines, so it's very confusing. But it's very, very important if you study chaotic mixing and particle transport. You would like to have a situation like that if you want strong transport of particles. But as you add the magnetic field, then as you increase the magnetic Reynolds number, you will see that the Lorentz force will back react in the velocity field and will quench the chaos in the velocity field a little as a function of eta. And then at this case, which was the last case of coherent large scale field I showed you, you have much less structures, and the maximal Lyapunov average Lyapunov exponent is lower. So these lines are barriers to transport in the velocity field. If you want to study passive scaling, it's a good tool to study it.
Axel, what do you think? Is it similar to normal models of dynamo that field increase and chaotic portion decrease?
I'm not sure. I mean, you say that. Why do you say that? I mean, it becomes less chaotic.
Because B equals 0, the chaotic, say, at least Lyapunov exponent larger.
Yes.
And it tends to something. So plausible then for strong magnetic field, it will be just 0. Is it true?
Yeah. I mean, the Lyapunov exponent is suppressed.
Yes, it's suppressed. That's
It's the same in the usual calculation for dynamos?
I think so. Yes. But I mean, note also that it's not strongly suppressed.
well, this is just.
I mean, I think it's just suppressed as B
It's
equals.
if you
becomes
check
comparable to
the
B.
average, it's not so smaller. But if you check the structures of those material lines, they are very different. So if you drop a particle here, it will stay locked here for some time until it can escape through the crossing of red lines and green lines. Here, they are always crossing, so the particles are always crazy here. Okay?
Little less crazy sometimes.
No, yeah.
Can you say actually how big is the magnetic field in terms of the kinetic energy here?
Here it's about the same. Kinetic energy and magnetic
That's when
energy.
the dynamo saturates. That's dynamo, I think, yeah? Right, so it's saturated.
And you have anisotropy emerging in this case, of course. You have X and Y, this is the magnetic field, is like this, and X and Z is like this. The same for the velocity field. So this doesn't look like a ABC flow. Okay. Although you can notice that the typical spatial scale is still there, because you have 5 vortices, because it's k equal to 5 is the average rhythm, so it's 5 somewhere. But here it's totally messed up.
So what do you plot here?
This is the streamlines of two-dimensional cuts of your 3D box. Okay. So if you cut an X parallel to X and Y, then you see something like this. And if you cut X and Z, then it's like this is just an isotropy of Sorry?
So B is for magnetic field lines? Or what?
Yes, magnetic field. Yeah.
Just for
Intensity.
dx dy, right? So that's
Yeah. Sure. Yeah.
not real. So what do you know from this theorem?
What we learned that the chaotic mixing is quenched when you increase the magnetic energy. Increase the magnetic field, you have less mixing of passive scalars. Okay, so they will have more coherent orbits, movements.
I mean, but it's kind of obvious, but now what we learned from this picture what you showed previous.
Oh yeah, we can show you. What I was interested in is in these structures. Yeah, they can be a prison to particles in these regions. Okay? You can. It's like well, we have magnetic trapping, right? This is not magnetic trapping. It's a different type of trapping. I don't know how to compare that, but particles can be trapped here in those islands.
Aerodynamic property.
Yeah.
But this is effect we have described by Craig.
Right.
Threatening of particles.
Right. some manifold which attract particle, and they rotate many times, and sometimes jump. It is strange attractor in some sense.
Yeah, but it's, you cannot call it an attractor because it escapes. So it's more like a non-attracting chaotic set.
But in general, it's attraction.
You know, there is a structure, and it's called chaotic saddle,
Good.
which
Yes,
is not an attractor, but it's chaotic. It's chaotic saddle, but it's not attractor.
But it rotates many times and jump.
Yeah, yeah, that's it.
Conformation of flux tubes, you know, what mean?
I don't know.
Physically,
I don't know.
what is the physical meaning of this? You know?
I have just done this, and it's not published yet. I'm thinking about it yet. But I wasn't sure because it's a beautiful picture.
Similar to carbon.
And then you have the spectroentropy. Spectroentropy, basically, you get the energy of each Fourier shelf. You compute this energy here for each value of k, normalize it, and then you insert, and this is like Shannon entropy's formula. And then you have minimal entropy would be an order state when you have p equal to 1. For some k, you have p equal to 1. Where is p? P is here. Okay, all energy is concentrated in one wave number, okay? Then that's totally spatially coherent. There's only one wave number. If you have energy evenly spread through all wave numbers, you have a noise. Okay, that's maximum energy. So if you check, forget about this, for instance, for a moment, and go to this. This is the first intermittency, right? On off. You check the spectroentropy. It doesn't tell you much. Because you have here a minimal, no magnetic energy almost. And then, oh, look at this. This is magnetic entropy, spectroentropy. I got the magnetic spectrum and computed the entropy. It's totally incoherent, as much as this. So there's no difference. Why? Because although the energy is very low, the spatial structures are still very complex. But if you look at the other intermittency, you see, every time you have a strong burst, if you look at the spatial patterns at this time, you'll see a very coherent state. And then this is the breaking of the state. So the entropy goes up when you're breaking, and goes down when you have coherence. So it's a very different thing. Okay. Well, I think that's enough. This is just results for 128 square.
Is it possible to show the magnetic energy in saturated state versus magnetic velocity? Do you have such? Magnetic energy in saturated state
Yeah.
versus magnetic velocity.
Magnetic. Oh yeah, the beginning.
Yes.
Okay.
So when magnetic velocity number about 10, yeah? So you have strong decrease. Yeah.
You mean, yeah, well, yeah.
What's the reason?
So in that sense, Axel, you said that this is catastrophic tension, yeah?
I'm saying this because in this system, the magnetic helicity is a conserved quantity. It can only
Yeah.
work resistively.
So there are no here flux of magnetic helicity.
No.
Is it possible to organize in such simulations flux of magnetic helicity? Just changing boundary conditions? Or
Yes, yes.
It's possible, yeah.
And what happens is that the dynamo is then losing its amplitude proportional to this Rm, 1 over Rm. The energy is decaying like 1 over Rm.
It's very interesting, Axel, because another possibility that we remember that in ABC4 we got windows of generation, and I remember that one of the boats window close to 10. Am I right?
Yeah, but
So what the question is, what it's actually this so-called some mimic of catastrophic convection?
but we had in simulation with Galante, we had a competition
in this.
No, but in this case too, of course, the magnetic energy is in equipartition. but it reaches a state only on a resistive time scale.
Mm-hmm.
If you then make the boundary condition open, the energy is no longer at equipetition,
Mhm.
decays like 1 over Rn.
Mhm.
Goes back to
Your idea to wait a little bit, it should derive to.
What?
Your idea to wait a little bit, to continue calculation and to arrive to some more high level, right?
No, it shouldn't change the
Ah.
boundary condition.
Just boundary condition, right?
No, I mean, what do you mean?
Maybe I don't understand you correctly. That you speak about resistive time. On
Yes.
resistive time, your idea that it will be larger.
On a resistive time scale, you reach a super equipetition field, which has the magnetic energy which is equal to the super equipetition of the kinetic energy by a factor of the scale separation.
So if we
So it's 5 in this case.
If you wait and we continue, to continue calculation in this situation, we will arrive to.
No, I mean he has already run long enough.
Have you
Yes,
shown
yeah.
the time evolution?
Evolution
This can be considered
I
stationary.
think you had it.
It is, yeah. Suppose this is the case. As long as you have 20,000. This is not, this is an intermittent. So after this, maybe this picture is better.
Yeah.
So it's not so intermittent, so it's easy to see that it's saturated, the red line.
So magnetic field is separate.
So this compressible calculation.
Compressive.
In addition to turbulence, we have acoustic waves, right?
Yeah, you could
Could look at this.
This is low Mach number.
Oh yeah, it's slow Mach number is 0.4 or maybe.
Nevertheless, we have some resonant oscillations here, right?
You have some, like
And
this
they
picture
can
shows
take,
you.
they can put some order in your, chaotic behavior.
About 5% variation of the density.
Well, it's not the sun, in this box, we have some also oscillations, right? So
Yeah.
you excite continuously.
Oh, you mean P modes?
Some oscillation modes.
Yeah.
And
But we
oscillation
don't-
modes can provide, again, structure.
Yes, I haven't measured the influence of compressibility on those oscillations. We don't know even how to do it.
But have a look at, that it has some acoustic.
I didn't check that.
Yeah, normally they are present. Yeah, normally you always try P modes, of course.
Yeah, but you have, there's some, the standing waves here, right? Because you have a periodic box, and then you excite some particular modes, and you keep particular long wave modes, because, short wave will decay in turbulence.
So you want to look at a K omega spectrum,
Can
right?
provide, this oscillatory behavior something. I don't know, but, that's.
Yeah, but I mean, these modes are weaker than the convection. P modes are small in amplitude compared to the convection which drives them.
No, not exactly, that it's still comparable. At least on the sun, the amplitude is not much different. Dynamics is dominated by acoustics, in fact,
But there's, I think, no evidence so far, from any work so far, that acoustic modes can drive dynamo action. I've not seen that in simulations yet.
No, they will not drive, because but they can, provide some order in this, that particular when they can see, this oscillating, it reminds me that.
And if you compare here, for example, time scale for random velocity field with acoustic time scale. So acoustic time scale is very small. Very small.
Very small.
In comparison even with turbulent filtration.
Yeah, I don't know what.
For such.
Time scale for, for say fundamental modes here.
Yeah.
Well, I don't know, but just asking.
I have another question. When you mentioned the Lyapunov exponents, they were in the mid-90s associated with the phenomenon of catastrophic quenching.
So I don't know catastrophic quenching. I'm not familiar with it.
Okay. I mean, it's simply the suppression of the dynamo. And you showed, as you go further to the right, the particles become trapped. And so this phenomenon was thought to be the reason for the fact that the dynamo becomes reaches less easily significant field strength at large magnetic resonance numbers. And that was a suggestion which was made by Hughes and Kim and maybe there was somebody else, Cataneo perhaps. And then, but that was not a predictive theory in any sense. And then subsequently came the idea that it can be due to magnetic helicity conservation, which was then providing a quantitative prediction, which was possible to be checked. And so I was wondering whether you have been trying to develop this early idea in terms of Lyapunov exponents again. No?
Not yet.
Mm-hmm. Okay.
Can you show your experiences in TensorFlow? How did you run it?
Sorry?
Can you share your experience with TensorFlow? Yeah, how did you run it? It's a big calculation here. So you used a parallel computer.
Yeah.
How you did it?
Like time series,
Yeah.
depending on the time, on length of it. 64 square, I use usually, since I always compute a bifurcation diagram with several values, then I chose to use a smaller number of nodes, like 16 processors to each time series, but then I could compute several time series in parallel, so several of those points in parallel. For each point of those, sometimes you have to compute several ones because you need to check the initial conditions if they affect or not the result, the end of the saturation of energy. Because at this point, it could be dependent on the initial condition. Maybe I didn't know, so I didn't have the experience with it. So I checked several. So it took me 4 months, 5 months of computation to generate this figure.
64 cube.
Yeah,
What
64
computer
cube.
you used? The cluster was
Yeah, the cluster.
16 processors. So it was
16. Yeah, I had access to more processors, but I decided to use 16 for each time series. So usually I have 48 processors for my use at the same time. So I use 16 for each time series, and then the time series could take 2 days to finish each time series.
Maybe you can say a few more words about how easy it was to learn
Well,
the code and
I was a bit scared in the beginning because of the size of the code. But once I started opening the code to check the routines, I thought it was very easy to follow it. Because I had checked, I was trying to find out what code I was going to use, and I checked the zoos and other codes. And I thought they were good but difficult to follow, the code, if you want to understand the code. And the pencil code was, I thought it was very easy. It was a huge code, but written in such a way that it looks like a small code. Because it's very well separated and routines.
So this is a big compliment.
yeah, we had sometimes comments among already experienced users that they were thinking the fact that there are so many different initial conditions is scary.
Yeah, because it's a code to do whatever you want. but yeah.
Do you think that was scary, that the fact that there were many different...
No, not to me. But I'm a computer scientist. So I don't know. I liked it. I liked it very much.
You try to check your results for different resolution?
Yes, it's the last slide, I think. So if you check, this is a suggestion by the referee of the paper. So I did it with 128. So this is a time series. The dashed line, the black is 128, and the red is 64 for this particular number only. I didn't check any others because I wanted to publish the paper, so just this one test. So the average value of the kinetic and magnetic energy seems to be the same. And these are the quantities. There's the entropy, spectral entropy, kinetic and magnetic, and this is another quantity with spectral energy. That's something else. So, well, I don't know.
What about the difference for bottom plot between the red and black?
Yes, because here red is 64. Yeah, I don't know why it's still oscillating, but it could be because when you increase the resolution, the tendency is to shift the whole bifurcation diagram. Like, you check this. Here. When you increase the resolution and those runs, the tendency is to shift this whole diagram, or whether to the right or to the left. Okay? So if you're near him and you shift it to the left, then you have intermittence here, an intermittence that you didn't have with 64 square, you have with 128. So you shift the position where the intermittency appears. So that's why the oscillation sometimes appear on those graphs. Okay? But what you have to look for is it still blowout bifurcation with intermittency that is the onset of contact? That's what you should look for.
There's some effect of numerical dissipation or numerical viscosity.
Yeah, you can have also that. I didn't check they didn't quantify the level of numerical dissipation.
But the critical Reynolds number doesn't change, right?
No, it does.
It does change.
If you increase the resolution, usually it does. Yeah. But the physics is the same. I mean, it's a blowout bifurcation with the same type of intermittencies. That's what must be found.
So if you follow up a series of resolutions, you should see some sort of convergence of the bifurcation point.
Oh yeah, if you no, I don't.
So this this 0.053. How much did it change when you went to 128 then?
I didn't go specifically on that because it was just after you mentioned it that I increased the resolution just to submit the paper quickly. But I have to do a more detailed work on that.
Yes.
It's kind of a classical problem, so people studied before. People with similar.
Yes, but with incompressible codes with k equal to 1, the forcing scale equal to 1. Not equal to 5, there's no mean field dynamo in their case, and it's incompressible. And they didn't focus on intermittency. Oh, just sweeten up big deal.
Have you checked the outcome of experiments, how they change if you change resolution?
So what the goal of this research? What we want to get from here?
From here, let's go to the conclusions. So, bifurcation diagram. Well, first, I think it's the first bifurcation diagram for ABC flow dynamos with inverse cascade of energy. And blowout bifurcation is the bifurcation responsible for the onset of dynamo in this case. I think it's the first time this type of intermittence, coherent and coherent intermittence, has been reported, although some other people might have seen it.
You mean in time, intermediate? In time?
What?
The intermediate, you mean
Here.
radiation for intermediate time, in time.
The blowout bifurcation, no, the onset of dynamo.
Yeah. And but what
In eta, not time. Resistivity.
But the intermittency is in time. That's what we're questioning.
Well, intermittency is in time also, but also in eta. Have both. In Reynolds, yeah. And this is already known. Chaotic mixing is dampened with the increased amount of energy. Spatial complexity of B and U fields decreases with the onset of B field dynamo, but subsequently increases with Reynolds number. I didn't show you this, but it's there. And we skipped because of the time. We skipped this one. Some open questions. I don't know if this can be found in other systems. It's not amazing. If it's present in turbulence with rotation and shear, and what causes it, I have a theory based on voltage stability and living price. I have to just check that.
I think it might be some confusion related with terminology. Because in principle here you study generation of large-scale magnetic field. So we study here mean field effects. On the other hand, intermittency is usually related with a small-scale dynamo.
Yeah, but here you have a mix.
So you believe that here you have combination of large-scale and small-scale dynamo?
Yeah, I do. Yeah. Well, you have, what I know is you have a large scale dynamo with intermittence, right?
It's just no, but you don't have magnetic operations when you have zero mean magnetic.
Zero mean magnetic field, zero.
So in principle, small-scale dynamo calculations not with that.
chaotic.
Yeah, but when you speak about intermittency, you speak about the you analyze.
Maybe if you see this times.
Yeah, I understand that.
Another one that
is here is another phenomena which we.
And another phenomenon too.
Yeah.
Here you have a zero mean
Really,
field.
this, but another phenomenon.
So this is the components of magnetic field. You have large scale fluctuations, but also small scale fluctuations.
But intermittency is related with large scale field.
Yes, this. Yeah.
That's why I said. So it's so my advice is explain this more carefully because people usually
Yes, they
in
think in terms of both small scale. Yeah.
in relation with intermittency they think about small scale.
Depends on the community. Since I come from the chaos community, it's
Yeah,
easy.
I understand.
But yeah, you're right. I should explain.
Since you speak.
I mean, that's what I said during
Am I
coffee.
right?
I said during coffee that this was the first time that mean field dynamo was studied with a direct simulation. It has been done so far. I mean, the intermittency of a mean field dynamo
Yeah.
with three-dimensional direct simulation. It has been done in the past in the framework of mean field models. And so there's no.
Yeah, there's a work by Sweet and Art. They studied intermittence, but only on ARF, not the other one.
By whom you mean? Say again.
Sweet and ARF. Sweet and Art. Art.
Yes.
It was art.
Yeah.
You mean Ott?
Yeah.
Ott from Maryland.
Maryland.
Yeah.
He did, yeah, so
Yeah,
compressible simulation. Low Reynolds number, very low Reynolds
Yeah.
number.
It's another one, not from Copenhagen.
And what is actually the relation between mean field, between the intermittence? What is known about the intermittency of alpha squared dynamos? Normally one is looking at alpha omega dynamos. So how about alpha squared dynamos, mean field dynamos? What is known about the bifurcation
Alpha square?
of
No,
the intermittency in those cases?
not much, because it all usually the studies on that focus on bifurcation diagrams and diagonal simulations and dynamic simulations, they don't focus on intermittency. They focus on and growth of growth rate of magnetic fields and the fast dynamo probably. I don't know any work like this. Let me see.
Look at magnetic kinetic electricity.
Didn't check it. Actually, I did, but I dropped the results. Yeah, I have a picture. Yeah, he mentioned it. I remember now. Because I showed it to my proctor. I said, hey, you think I can have some relation between alpha effect and the elasticity here? And he said, oh no, forget about that because you don't have a mean view here. This is direct simulation and high Reynolds number. So the connection is very unclear. Forget it. So I didn't include that.
We all would be very interested to know about that.
Is it possible here to apply test field method in order to calculate mean field coefficient? This
Yeah, it
question
has
to
all
you.
been done for turbulent homogeneous dynamos in exactly the same setting. Yes, the answer is yes, and it has been done all of last year. Is there differences? Of course, we use turbulence, not the ABC flow. Now, one question would be, is there actually a difference between the two? Do you
Sorry,
think
I
so?
missed the beginning.
Is there actually, my question is then, is there a difference between the work that has been done on random forcing, delta correlate in time, as opposed to steady forcing with ABC flow?
Well, I don't know, because in the beginning I was trying to, I thought about using that random correlated noise. But I thought, well, this is too complicated for my first work on that, so I chose the easy flow. But I don't know.
Yeah, but for example, if you plot phase portrait, so this is just a question: what is the difference between turbulence and chaos in dynamical system? So I think that if we have turbulence, phase portrait will be filled completely. But for a dynamical system with a chaos, you will have some spaces which are not filled by points, trajectories of particles. Maybe this is a difference.
Yeah, but this is
Is it correct
this is
or
for
not?
low-dimensional chaos, and when you have the high-dimensional chaos, then
Yeah.
the picture becomes blurred.
And nevertheless, if there is a strong chaos, I think it's possible to distinguish between turbulence
Oh, it is.
and chaos.
Igor, expression is low dimension.
But the way they distinguish it is through the scaling laws of the power spectra. It's not.
So it's
so
different.
because you don't have -5 thirds and